So the next step after we finish our preparing our parameters and our we've obtained our .efp file from the game's input, and we have the XYZ file for our system. We can directly prepare our libefp input file if we want to run an EFP calculation. So let us look at a sample libefp input file. So this is what a sample EFP libefp file looks like. So we start from the very first sentence. So the first section contains all the simulation settings that we require to run EFP calculations in LibEFP, which is the software library that we use. So run type refers to the type of job that we want to run. So SP would refer to a single point energy calculation. The coord points would indicate that we enter the information of all the atoms in the form of XYZ coordinates. Terms indicate what type of interaction energy components we want the software to calculate. So this would indicate that we want the electrostatics, the polarization, dispersion, and exchange repulsion to be calculated. Elect damp, Paul damp, and dispersion damp would refer to the type of formula that we want to use in order to calculate all the damping parameters. Enable cutoff true would indicate the specific cutoff or the specific distance beyond which we can assume that there would be no EFP-EFP interactions between two fragments. Enable PBC in this case is false. If we want to run a simulation inside a periodic box, we can just turn it to true. Enable pairwise indicates that all the pairwise interaction calculations between any two fragments should be turned on. Ligand refers to the specific fragment that is considered to be the central ligand and with which the interactions of all the other fragments are calculated. So ligand 0 would indicate the very first fragment, or the fragment, the first fragment, which is basically the ligand in this case. So we calculate the interaction of this fragment with the second fragment, with the third fragment, and the fourth fragment. And symmetry is equal to true would indicate that the symmetry unique systems would be taken into consideration while we are doing the EFP calculation. Okay, so now we go to the second part, which actually refers to the geometry of our system. So in this case, just let me go back and show what the system file looks like in this case. So this is the benzene.xyz file. So it contains 48 atoms. So this is basically a benzene unit cell, which contains 4 benzene molecules. So we're trying to calculate the interaction energy in a unit cell of benzene. So how we use this to calculate or to prepare a libefp file is that we take the first 3 atoms and paste the coordinates, the XYZ coordinates of the first 3 atoms of each fragment under the name of each fragment. So for this case, the only unique fragment that we have in our system is benzene. So fragment benzene, which is the first fragment, would have the coordinates of the first 3 atoms. Similarly, the second fragment would also have the coordinates of the first 3 atoms of the second fragment. Fragment 3 and 4 would subsequently have the atom coordinates of the first 3 atoms. So once we've prepared that, we can get our libefp input file. In case we have a lot more than 48 atoms, in case anyone has 10,000, 20,000 or more atoms in their system, then the most ideal way of preparing this libefp input file instead of doing it manually would probably be to prepare a Python script, which can run to generate a libefp input file by extracting all the atom coordinates from the .xyz file, because it would not be manually possible to calculate everything by hand. Another very important factor that should be taken into consideration while we are preparing the libefp input file is that once we mention the name of any fragment, so in this case, when it says fragment benzene, when we turn on the BFP, when we turn on the EFP calculation and we actually run the EFP job, the system would look for a .efp file with the same name as that of the fragment name. So it will look for a file called benzene.efp. So we have in this directory, we have the file called benzene.efp. So we just open that file in the VI editor to take a look at it. We also have to ensure that the frag name section in our .efp file has the same name as that of the fragment. So in this case, we will have to change this to benzene, which is our fragment name. So this has to be taken into consideration every time we do an EFP calculation. It's imperative that we, if the names are not the same, it's imperative that we change the names of frag name and the .efp file in order for the EFP job to be terminated successfully. So now that we're done with that, we'll go back to take a final look at our EFP input file. And since everything looks in order, we can just run an EFP calculation, simple EFP calculation on our unit cell and analyze the output. So the way to do that would be to use the driver called EFPMD. So the way we would do this would be EFPMD, then name of our input file, which is benzene.libefp.inp, and we store it in the file called out. So the job has terminated because EFP, being in effect a classical calculations, takes a lot less time to finish running. So we just open the output file. So we see that in the beginning, it contains the publication references and the project website. And then we start with the simulation settings. So a lot of these settings are specifically what we mentioned in an input file. There are a lot more extra information pertaining to the simulation settings that are basically taken as default. So the output file will mention them explicitly, but we do not explicitly need to mention them in our input file if the default is exactly what we need. So this refers to the type of job. So this is a single point energy job. So geometry in angstroms would indicate the geometry of our system. So we would have 48 atoms here. And then the specific section that we're interested in is the pairwise energy analysis. So here we have the pairwise energy analysis between each fragment and the ligand. So the first section is basically the pairwise energy interaction between fragment 0 and ligand 0. Fragment 0 is basically the ligand, so it's the interaction of the fragment with itself. So hence, we see that the pairwise energy is 0 in this case. Then we have the pairwise energies between fragment 1 and ligand 0, which is, as expected, a non-zero value. And so are the interactions with fragments 2 and fragment 3. So after calculation of all the individual dimer pairs are done, the system will print the lattice energy components, and finally the pairwise energy analysis, the completed version with all the total energy components for electrostatics, polarization, dispersion, exchange pulsion, point charges, charge penetration energy, and the total energy. And finally, a statement that tells you that the job has been completed successfully. And that's it.